chapter 3. First lecture on two-dimensional motion and vectors. Okay, so part of what we'll be looking at, there's a picture in the book of a helicopter dropping an object as it's flying along. And the question is, as it falls, as it goes along, and suddenly drops something out, what is the path of that object as it falls to the ground? Does it go straight down as the helicopter moves on? Does it go backwards because of wind resistance? Does it go for a while and then fall? Or does it take some other kind of path? This is part of what we see in chapter 2, because in chapter 3, I should say, in chapter 2, we dealt with motion in the x direction, and separately motion in the y direction, where left is positive, right is positive, left is negative, up is positive, and down is negative. But the difference between these is in the x direction we have no force of gravity, but in the y direction acceleration is g, which is minus 9.8 meters per second squared, but for a lot of the problems I do, we'll be using g is minus 10 meters per second squared. Okay? So it turns out happening because the object is actually moving at a constant speed, or constant velocity, I should say, because there's no gravity. So once it lets go, it's going to move constantly this way, but it's going to be accelerating downwards. What it'll actually do is follow a parabolic path. So the path will actually be a parabola. And this is actually discovered by Galileo back in the early 1600s. Prior to that time, it was thought the objects, when they were sent off like a cannon, it would be something where they'd actually thought it did something like this, got tired, and then suddenly fell down. Well, that's not how objects work. They actually travel a parabolic path. So you shoot it with a particular velocity, v0, and it's going to follow a path. At the angle that you shoot it at will be that. So this is also part of one of the labs coming up. We'll get to those. So for this first part of the chapter, I'm only going to deal with vectors. I'll talk about two-dimensional motion in the next lecture. So that's what we're going to be doing here. So the first part here will be just strictly on vectors. There's a bit in doing this, but what I'm going to be doing is giving this how you can solve for vectors using a graphical method. And the best way to do this will be using a protractor of some sort to solve these. So, and there's a program on PhET, Physics Teacher Education from the University of Colorado. There's a link on chapter 2 and 3. As far as there's links in there as far as that. And these have different simulations. They're all free. And the one we're going to be using is called Vectors. It's under Math. And we'll be going through that here. So you can use the simulation. Part of what I'll try to do is post a couple simulations related to the video, related to the lab, as far as that's concerned. So I'll post that in a little bit here. All right. First thing is when we have vectors, we define it in the x, y direction. A vector is always going to be defined as these direction, let's say R, and the angle is above the horizon, above the positive horizontal axis. And what we'll have for the first one is, so say we have R is 10 meters, theta is 30 degrees. Now we have that, we have X and Y. X, I should say Y and X to be consistent with our coordinates. So X will be equal to R times the cosine of the angle. Y is equal to R times the sine of the angle, as far as that's concerned. So in this case, X would be 10 times cosine of 30 degrees, which is, then this is 0.866, so this would be 8.66 meters, roughly. This would be 10 times the sine of 30 degrees, which would be, that's 1/2, so this would be 5.00 meters. So that's it there. So that's how we do a component method that way. What we also can do, so if you have different vectors, depending on what the angle is, so if you have this, let's say R is 10, and this angle is 120 degrees, then you would have, then R is 120 degrees, then we would have, this would be cosine of 120 degrees. This would be the sine of 120 degrees. Let's see, the cosine of 120, that'd be, let's see, that would be 60, that would be 10 times minus 0.5, and sine of that would be, oh, plus I should say, this is still vertical, this would be minus 0.866, so this would be 5 meters, and this would be minus 8.66 meters. So that's what this, with distance here, this would be minus 8.66, and this would be plus 5 meters. So that's how you do that part. Now, suppose you want to add two vectors. And I will show you this in the simulation software in a few minutes here. So if you want to add two vectors, say you've got this vector and that vector. This one is A, and this one is B, all right? So it could be that it's two forces pulling or whatever. So in this case, when you're adding vectors, what we have to keep in mind is that vectors, say we have a vector A here and a vector this one, if we move it but keep the angle the same and the length, all we do is slide it, these two are identical. And when you're adding vectors, what we're going to prefer to do is to add this in the graphical method. So the way you would do this is the result would not be that, all right? That is not the case. You don't just add the tail. What you have to do is it's tail to head, tail to head. So we'd slide this one up here, and then our result would be that. Or we could slide this one up to here, and the result would be the same. So this would be A, this would be B, and we could draw the vector across there. So that's how that would work there. We could do it as component methods, but adding vectors this way is a lot simpler. It's a lot more easier. We're not doing this as an engineering class, so that's how we're going to do it. So if we have another one slightly more complicated, say A, B, and then C, well, what we do is we slide A, B over to here, and then A over to C over to here, and this would be, so tail to head, tail to head, tail to head. So this is B, this is C, this is our result. So the next part here is I will show you how to do this using the PhET program. Part of lecture chapter 3 on vectors, we will be using this PhET vector simulation, which is free. Click on the link for chapter 3 for that. We'll be going into lab, and this is the simulation we'll be using. It has an XY coordinate system. Nothing with the grids marked, and we'll be looking at vectors. So what we're going to be doing is starting with some arbitrary vector like that. We put in the grid, then, and we put in the values. The length of this vector is 22.4. The x component is 20 meters or so, and the y component is 10, and the angle is 26.6 degrees. If we get rid of that and just leave this the y, that, so we don't have the xy labeled, that's a component. Notice if I move this anywhere, the values up here do not change. Right? No matter where I move it, as long as all I do is slide it around, then it's going to be fine. So that's that one. All right. I'll bring in a second vector. All right. And this one is just arbitrary. Tan is an angle of 36.9 degrees. X component is 8 meter, 8, and the y component is 6. All right, now, we could do is add this as a component method. So suppose we want to add this vector to that vector. All right, we both have both at the origin. Again, the sum of these two is not from this point to that point. It's from tail to head, tail to head. So how can we do that? All right, the way we can do this is, the best way is we draw that one up here, and then we add the sum, and there's our sum, and we can see that the sum of these two is 32.2, and the angle is about 30 degrees. X is 28, Y is 16. So that's the sum of these two. And notice if we change this, right? Now the only time the two are going to be, when it adds up, is if the two are exactly in the same direction. If they both A and B have the same angle, the result will be the sum of the two. Right? So now if we change this around, here's our result as far as that's concerned. So that's the easiest way to, in my opinion, to solve addition of vectors, is by using this program or using a protractor, measure out tail to head, tail to head. All right, so let's clear this. All right, let's try doing 3. There, we got this one. And let's do it let's put this one here. All right, let's add another one. Let's get rid of the sum. Let's add this one like that. 10 going that way. And then a third one, we'll add third this way. So let's have them all coming out at one point. Let's do it this way. All right, what would be the sum of all those? All right, the only way you can do this is we do tail to head. And it doesn't matter which order they're in. And then tail to head. And we do the sum. And there it is. So it would be 11.3. Tail to head, tail to head, tail to head. So that's how you would add these graphically. We could do it as components, but it gets more complicated trying to do each one of those. So this is how I advise you would do this. The simulation program works really well for that, as far as that's concerned. Again, the angle is always defined as relative to the x-axis. So let's try one more, just so you can get an idea what I mean by the angles here. All right, so, oops, get rid of the sum. All right, here's our angles. Notice here is 90 degrees. It's 45, 135, 180 degrees. So that's how the angle is. So as we go from is vertical, then x would be 0. If we go past 90 degrees, then x is going to be negative, right? And if we added one more to this, and add the sum, again, tail to head, that's going to be the result. There. All right, so that's how you do vectors. Depending on how arbitrary they are, this is how you can do a lot of problems using this simple simulation program. So, thank you.